Hi, everyone. In this lecture, I'd like to talk to you about sound and sound waves. So, as a reminder from the last lecture, sound waves are longitudinal waves. And what that means is that the oscillation of the medium is parallel to the direction of propagation. Now, these waves are actually compressions and expansions, which is sometimes called rarefactions, of the media that they're traveling through. And you can think of this as kind of a pressure wave. So let's examine the image here on the left. You can imagine that there's a sound wave traveling through air in a tube, okay? Now, the sound comes through the end. Maybe there's a drum or something that gets beaten at the end of this tube, something like that, to create the sound wave. And then what happens is, as the sound wave moves through the air, the molecules of the air get close together and then further apart, okay? This is supposed to be a pulse of sound traveling down. And so you can see that the air molecules are really densely packed right here and then spread further apart here. And then as it travels down to the tube, here the velocity of the wave is to the right. Then after the densely packed part passes through, then you have that rarefaction or less dense air behind the wave, okay? And it's traveling to the right through here. So that's really a pressure wave. And it's a pressure wave caused by the vibrations of the atoms in the medium. Now, here's some interesting facts about sound. The pitch, or how high or low a sound feels to you, is related to the frequency of the vibration. A higher frequency of vibration results in a higher perceived sound, and a lower frequency of vibration is a lower sound to you. Most humans, or humans as a whole, can hear between 20 to 20,000 hertz, and that upper limit, the 20,000 hertz side, that really decreases as you age. And then we have ultrasonic, you might have heard of that, and that's above 20,000 hertz. So that's outside of the range that humans can hear, but dogs, of course, can hear higher frequencies than humans can hear, so they can still hear that, which is how dog whistles work. And then infrasonic is frequencies below 20 hertz or so, okay? So those are lower frequency sounds. So in the human ear, in the human ear, this is a little schematic of the ear. What happens when you hear a sound is that the sound waves actually are kind of funneled in to your ear canal by the shape of the ear, and then they travel down the ear canal to the eardrum, which is right here, okay? The eardrum will vibrate in response to the oscillation of the pressure wave incoming to the air, of the air. And then that oscillation of the eardrum causes these tiny bones in your inner ear, the hammer, anvil, and stirrup, to wiggle. And then that wiggling it hits your inner ear right here. So here's your inner ear. And then the cochlea in your inner ear transforms those mechanical vibrations of these bones into electrical energy and then sends those electrical signals to your brain, okay? Now there's more to it, and if you want to know more about it, you can read more about it in your textbook. The loudness of the sound is a combination of the intensity of the sound, which is of course due to the amplitude of the sound wave. So it's that, but it's also mixed into the human perception, right? And we'll talk more about that in a second. So the loudness is really the human perception of the intensity of the sound. And intensity is how far the atoms in the wave wiggle, right? Which is dictated by how much the source moves. So how hard you hit the drum dictates how much the drum wiggles back and forth, or how hard you pluck the string of the guitar. That can help dictate the amplitude of oscillation of the air molecules surround it, which dictate the perception of the loudness of the sound, okay? Causes the air molecules to vibrate more. But loudness has human perception in it, and so it's more complex than just the intensity of the sound. Remember, we talked about intensity in a previous lecture. So humans actually can hear over a very wide range of intensities. This plot here shows from what we call the threshold of hearing, which hits at around 10 to the minus 12 watts per meter squared for the intensity, and it plots it all the way up to 1 watt per meter squared. Now, you can hear intensities louder than 1 watt per meter squared. But at around this level, it's called the threshold of pain. This is where it really starts to hurt. And if it gets louder than that, of course, then you can really start to damage your hearing. Now, you'll notice here, there's these red lines on this plot, which plots the frequency on the horizontal axis versus the intensity on the vertical axis on the right-hand side. We'll talk about the left-hand side in just a second. But for now, let's just talk about the frequency versus the intensity. You can see that these curves, what they're doing is translating the intensity into sound level at different frequencies, okay? Now you can see that the threshold of pain is shown here as this wiggly curve that starts here on the right at a high value and then kind of drops down and then goes back up, okay? So that dependence on the frequency is an interesting characteristic of human hearing. High and low frequencies are perceived as louder than mid-range frequencies. So there you go. So these curves translate that intensity into human perception. Now, since our hearing does span 12 orders of magnitude and intensity, and it intertwines perception with measurable quantities, what we usually do is talk about a sound level in a unit that's called the decibel. Now, this actually comes from the unit, the bell, from Alexander Graham Bell. But since the bell is not as useful a unit as the decibel, which is 1/10 of a bell, we usually use decibels. So we define the sound level in decibels as beta is equal to 10 times the log of I over I naught. Now here, I is the intensity of the sound, and I naught is a reference intensity, which is usually 1 times 10 to the minus 12 watts per meter squared, or the threshold of hearing. And then we multiply that times a 10, okay? So here's some examples of that, intensities of various sounds. You have all the way up here to very, very loud sounds that could damage your hearing, such as a jet plane or a loud rock concert, right? Those are at 140, 120 decibels respectively, all the way down to a whisper and a rustle of leaves. And those are in intensities of 10 to the minus 9 and 10 to the minus 11 watts per meter squared. So let's just take one example. I picked a siren. If you're standing 30 meters away from a siren, like a, I don't know, fire truck siren or something, that has a sound level that's reported as 100 decibels. And we'll agree that this is a pretty loud sound, but it's not going to damage your hearing if you're 30 meters away, right? Now, the intensity in sound level in decibels is 100, and the intensity in watts per meter squared is 1 times 10 to the minus 2. So how does that work? Well, here you say you have beta, which is 100 decibels, and that's equal to 10 times the log of 1 times 10 to the minus 2 watts per meter squared, divided by 1 times 10 to the minus 12 watts per meter squared. Now, when you do 10 to the minus 2 divided by 10 to the minus 12, you get 10 to the 10th. And this is a base 10 logarithm. It's not a natural log, it's a base 10 log. So when you take the base 10 log of 10 to the 10th, you get 10. And then you have the 10 out front times the 10 inside, and that gives you 100. So that's how that works. So you have 100 decibels is 1 times 10 to the minus 2 watts per meter squared. Now, an average human can detect a difference in the loudness of sound of just 1 to 2 decibels. So, you know, decently sensitive, I guess. Sound can travel through any kind of matter, but it can't travel through a vacuum, no matter what your sci-fi movie says. The speed of sound is different in different materials, and that's shown here on this little speed of sound in various materials table. So you can see here the air at 0 degrees Celsius is 331 meters per second. But then the speed of sound goes up as the density of the medium goes up, okay? So in general, the speed of sound is slowest in gases, and then it goes faster in liquids, and fastest, of course, in solids, because the more dense the medium, the faster the speed of sound. I'll show you an equation for that in a second. The speed also depends a little bit on temperature, but that's especially true for gases. It's actually a faster speed, 343 meters per second at room temperature versus at 0 degrees Celsius. And there's an equation that we have to describe that in a second. So the speed of sound in a medium depends on the properties of the medium. And in general, we can write it this way, that the speed of sound is going to be equal to the square root of the elastic property of the medium, usually defined by the modulus, divided by the inertial property of the medium, usually defined by the density. What's happening in sort of a nanoscale view is that, let's say that you have these atoms in a medium, and the wiggling of one atom in the medium causes its neighbor to wiggle, right? Especially in a solid where you've got that kind of ball and spring model of how atoms are hooked up in a solid, where you have the balls or the atoms, and then the bond in between the neighboring atoms is the spring. So you can imagine that if you wiggled two things that were connected by a spring, then that would make the next thing wiggle, right? And so you can imagine that the heavier, the more dense the medium, that would affect the speed of sound, and that the elastic property, or how tightly the neighboring atoms are bound, would also affect the speed of sound. So the speed of sound in a solid, the modulus that we're going to use is the elastic modulus, and we'll call that E, okay? And then the density of the material in terms of the mass per unit volume, and that's, we're going to say, is rho. So the speed of sound in a solid is approximately equal to the square root of the elastic modulus E divided by the density rho. Now for a liquid or a gas, the elastic modulus, remember, is a property that's measured by, say, taking a metal bar and grabbing one end of the bar and then grabbing the other end of the bar and stretching it out. Now you can't do that. You can't stretch along one axis for liquids or gases. It's just not possible, but you can put them under pressure. And under these situations, we define what's called the bulk modulus, okay? So in the bulk modulus, you put it under pressure and you look at how much the volume changes in response. So the bulk modulus of the material we'll call B, and the density of the liquid or gas is rho again. So the speed of sound in a liquid or a gas is approximately equal to the square root of the bulk modulus divided by the density rho. Now, as we discussed, the speed of sound also depends some on the temperature of the medium. And this is particularly important with gases. We're not going to cover all of the ins and outs of that here, but it has to do with the fact that the density of the gas actually changes as the temperature changes because of the ideal gas law. So for air, the relationship between the speed of sound and the temperature is approximately given by 331 plus 0.6 times T. And this is in meters per second. In this equation, you should plug in the temperature of the air in Celsius in order for it to work. Otherwise, you need to convert to Celsius first. 331 meters per second is the speed of sound in air at 0 degrees Celsius, as you might remember from seeing in a previous slide. So here's some speed of sound in gases for some examples. Hydrogen, 1,286 meters per second. You can see that. And then air at 20 degrees C, 343, air at 0 degrees C, 331, oxygen, 317. So these speeds are all in meters per second. Okay, let's do an example problem to kind of put all of this stuff together. So what's the wavelength of a 2 megahertz ultrasonic wave in aluminum? Okay, so you can look up the elastic modulus of metals and their densities in various tables in your book and elsewhere. And so the elastic modulus of aluminum is 69 gigapascals, and the density of aluminum is 2,700 kilograms per cubic meter. Now remember your SI prefixes here. 2 megahertz, a mega is 10 to the 6th, so that's a wavelength of 2 times 10, or I'm sorry, a frequency of 2 times 10 to the 6th hertz. And the elastic modulus is 69 gigapascals. Giga is 10 to the 9th, so that's 69 times 10 to the 9th pascals, okay? All right, so let's put all this together. Remember that the speed of sound in a solid is the square root of the elastic modulus over the density. So that here is the square root of 69 times 10 to the 9th pascals divided by 2,700 kilograms per cubic meter. And that's equal to 5,055 meters per second. We should do 2 sig figs here, but I like to keep all my decimals and then round at the end. So that's what I'm going to do. Now this speed is also, remember, equal to lambda f, the wavelength times the frequency. That's always true for waves. You can say that v is equal to lambda f is always true. So you set that equal to your 5,055 meters per second for your speed, and then that's equal to the wavelength times the frequency. The frequency was given as 2 megahertz, or 2 times 10 to the 6th hertz. So now you can divide both sides of that equation by 2 times 10 to the 6th, and end up with a wavelength of 2.5 times 10 to the minus 3, or 2.5 millimeters. So that would be the wavelength. Okay, well, I hope that all made sense. I hope you understood it, and I'll see you in the next lecture.